we will describe several CDRs topology in a 3D system. In this video, we are going to show the image of why we need a good jitter tolerance JTOL in a CDR operation. Before talking about the jitter tolerance, let's review the jitter as a case study and see how the TXPO's jitter would impact the simulation operation. First, assume the clock to Q delay in the flip-flop is 0 for simplicity. Then, the output data D-out's transition time will align with the clock CK's rising edge in the ideal phase position. If the clock phase is not static all the time, the clock phase could be sometimes earlier or sometimes later than the ideal phase. Then we call this phase uncertainty jitter. Obviously, the clock's jitter would directly translate to the output data's jitter. If the transmitter's output jitter is too much, the RX sampling point will be most of the time close to the transition and get a high bit array. Does that mean the fundamental clock jitter requirement from the TXPO must be a very low jitter or even zero jitters ideally over frequencies? Think about the CDR tracking images for 5 seconds. Bingo! Of course not. Let's understand why the CDR's phase tracking to the TXPO phase is good for a less bit array if we would have a perfect CDR tracking. Since the CDR would perfectly track the TXPO's phase, no matter the phase of the input data transition, finding RX is moving. The CDR's aligned clock will always align the input phase, which means the phase error between both the input data, finding RX, and CDR's recovery clock, phi CK, is 0. Then the phase difference between the retiming clock, phi CK sample, and the input data, phi D in RX, would be 1/2 UI. In other words, the RX would always sample the input data in the middle of its eye, which provides the maximal timing margin and minimal bit array if both setup hold times are equal. After understanding the perfect tracking, what's the impairment image of the real CDR tracking behavior? Think about the real response or tracking images of the CDR for 5 seconds. Right, speed or response time. The phase versus time plots of a real CDR's time domain phase tracking behavior show 2 cases of low frequency phase jitter at F1 and high frequency phase jitter at F2. If the phase of the input data moves slowly, the edge clock can align well with the little phase error and end up a perfect tracking. But if the input phase of the input data moves quickly, the edge clock would track in a slew rate limit, and the phase error between the input data and recovery clock is big. So, the sampling position is not in the middle of the eye and close to the edge to cause a high bit array. Besides the fast speed of the input phase, what else could be the limitation of the CDR phase tracking? Correct, amplitude. If the input phase moves too much at a certain rate, the CDR's phase will be slew rate limited as well, since it cannot equivalently track the input phase change quickly. In the time domain, we know the CDR can track the input phase at low frequency, but not the input phase at high frequency. Therefore, the CDR's output phase versus input phase transfer function is maximal at a low frequency and decrease at a higher frequency, which is a low pass response in the green dashed line curve. On the other hand, the phase transfer function of the phase error between output phase and input phase versus the input phase will be a high pass, since the CDR may track the input phase well and reject the input low frequency jitter. After understanding how the CDR's tracking behavior in the time domain and frequency domain, how do we evaluate if a real CDR has a good tracking behavior? Correct. Jitter tolerance, JTOL, is a way of benchmarking different CDRs. The idea is very simple. Just apply the jitter at the input of a CDR and check its recovery data's bit error rate under a certain value as a pass-fail criterion to capture the CDR's frequency response to the tracking behavior. The input jitter will be a sinusoidal jitter with a single frequency component FM and amplitude component AM. In a test setup, the CDR is stretched by applying sinusoidal phase modulation to the serial data stream. By using a jitter, the phase modulation depth AM and frequency FM could be accurately controlled and then transmitted to the device under test, DUT. The recovery data from the DUT was sent to a PRBS error checker to evaluate the bit error rate. We would meet the pass condition when the received bit error rate is less than the specified value from the standard, which is 1E-9 in DisplayPort over 1E-12 in tangent-based KR. We record a fail when the bit array is larger than the specified value. Even though the JTOL evaluation is tedious, the procedure is straightforward as follows. For each phase modulation frequency FM, we may increase phase modulation depth AM until the bit array is varying. For example, pick FM1 and AM1 and we pass the received bit array to the specified value. Then pick FM1 and AM2 and the received bit array passed. Finally, pick FM1 and AM3, but the received bit array failed. So we determine the maximum phase modulation depth AM is AM2 and stop the testing at the modulation frequency FM1. Then we could sweep the same procedure at other phase modulation frequency FM to determine other maximum modulation depth M. The CDR JTOL would be complete after connecting all the maximum modulation depth in the blue line. To make the ecosystem work in a series, most wireline standards will even define the JTOL mask as shown here. The CDR1 above the JTOL mask means it can tolerate more jitter than the standard specified value to meet the spec. On the other hand, the CDR2 can meet the JTOL mask at low frequencies, but not at high frequencies. Therefore, the CDR2 will fail the spec. Again, the CDR1's JTOL is better than the CDR2's JTOL. So, the CDR1 should provide a better transmission quality with a less bit rate than the CDR2 does. What else could be another benefit of a better JTOL? Think about the TXPL's jitter images for 5 seconds. Bingo! The jitter requirement of the CDR1's link partner at the far end TXPL can be relaxed a bit. For example, the CDR can well track the low frequency F1 sinusoidal jitter at the TX output or RX input. So the TX jitter does not hurt the bit array. the phase error between the RX input and sampling clock would be 1/2 UI, even though the TXPO's low frequency jitter is not small. But the CDR cannot well track the high frequency F2 sinusoidal jitter at the TX output over RX input. So the TX jitter hurts the bit array. The phase error between the RX input and sampling clock is much less than the 1/2 UI if the high frequency jitter is increased. Therefore, the low frequency jitter does not matter to the TXPO. For the SerDes, the TXPO's integrated jitter should be integrated from the bandwidth of the CDR to the next rate from the TXPO's phase noise. For example, Zoic-based standard apply baud rate divided by 1667 for TXPO integrated high-pass bandwidth corner frequency. Obviously, the CDR1's tracking bandwidth is much higher than the CDR2. Therefore, the jitter requirement of the CDR1's link partner at the far end TXPO can be much less than the CDR2's link partner. Even though both CDR pass the jitter tolerance mask. Here are the summarized images of why you need a good jitter tolerance JTOL in a CDR. Under a good JTOL in a CDR, the SerDes link will provide a better transmission quality with less bit array than a poor JTOL. Therefore, most standards even specify the JTOL mask for the ecosystem to follow. In addition, a better JTOL of an RX can relax the jitter requirement of its link partner at the far end TX to reduce the power, area, and design cost overhead in a SerDes system. Therefore, all the images of a test setup or verification of the JTOL are also shown in this video. Thanks for watching. Before you go, if you are benefiting from those circuit images, I would love to hear your feedback and please share your comments down below. Lastly, please share the video link with people who may be benefit from it.